but these are random numbers that we have. Go ahead, Eva.
So for age and education, you would say that there's not a strong correlation, but there is a significance.
There is some relationship, yeah.
But
It's
it's not strong.
significant. We use significant means that it's not by chance, by the way. We don't mean important.
And you
Correct?
know that because of the little asterisk.
So either look at the asterisk or here is the actual significance. 0.01 is less than 5%. That means that this number is significant. Look at its significance is less than 5%.
So if the sig
And
is less than 5%, then it is significant.
Usually you use alpha 5% or 1%, one of the two. Yeah.
So if it is lower than.
I have a question.
5, it's
Yeah.
So for the Pearson correlation, if you look on top, how the age and salary is negative .008.
Age and salary in here,
So that would be less than 0, correct? So how would you?
Now look at the absolute number. Absolute number is, let me put it in here so you can see. 0 in here, forget about the sign. Sign means the direction. So 0.008 is somewhere around this area,
Yep.
Isn't that less than 0?
But what about the negative?
No.
The negative means that
Different direction.
directional, as one goes up, the other one goes down.
But isn't .008 less?
It is very close to, yeah, actually, you may want to look at it this way. Okay, I think -1, +1 is 0. -0.008 would be somewhere around this area.
So you would still see if it's the closest, because that's closer to 0 than 1.
Anything closer to 0, and notice that it didn't come out significant. That means that just by chance.
Well, I just remembered you saying that there could be no numbers outside of the 0 and the 1, so I don't.
Yeah, outside of actually these two numbers. I said outside of the absolute one. So really, the numbers should be in this range,
Okay.
in this range.
Wait, so not 0 to 1 now, -1?
I'm sorry?
So should we disregard the 0 to 1? It's now -1 to 1? For the range?
It's absolute one, so it's in between -1 and 1.
Okay.
Yeah, anything less than -1 or larger than +1, these cannot be.
Okay, so,
The absolute number should be between 0 and 1.
okay.
So if you look at, let's say the one that Nicole was talking about, I'm looking at right now salary and age, salary age. You can see it in here, or salary and age, you can see it in here, it's a mirror image, correct? So you see that it is 0.008 and it is not significant. Look at the significance of the 95%. So that's why I didn't put asterisks over it. But here is the actual significance.
But that is not significant then, correct?
No, it's not. This is much
It's
larger
more
than 5%.
0.5.
So really, we don't really pay attention to the top number?
We just need the Pearson correlation to tell you the direction of the relationship and if there is a relationship.
And whether it's significant or not. Like this now one number is significant. Look at the significance. So this is real. There is a relationship between age and education. There is one.
Yes.
But when it comes to age and salary, there is no relationship.
Well,
That didn't come out significant. You just got shoe size and your cell number. You got 0.008. That means
So if it's not significant, there is no relationship.
that means there is no relationship. I'm sorry, Nani.
That's what I was gonna ask, so I was just saying, so first we look at the sig number, and then that will tell us if we even need to look at the Pearson correlation.
Correct. That's right. That.
Thank you.
So you see that what I'm saying that look at this. This is a little cluttered. The way that I have it on my handout is a lot easier to read. First of all, notice that the upper triangle above the diagonal is mirror image of this one. And then in each cell it has 3 numbers, Pearson, which you're interested in, the significance, and n. Look at the way I have it in here. I did not put the significance, I did not put the n, I did not put the upper triangle. Look how nicely mine is simple, easy to read.
But don't we need,
Except whenever something is significant, I have either put one asterisk on it or two asterisks. If it is not significant, I then put asterisks over it. For example, if you look at this, on age and salary, 0.19. Age and salary.
How do you know that's Asian, how do you know which one it's comparing to?
Now, remember, I have numbers to make it easy and clean. I have put
Ones, okay.
salary, number. On the top, you could have written salary, age, tenure, and education, but I didn't have enough space for these words. I put 1, 2, 3, 4. 4 means education, 3 means tenure, 2 means age and salary. So relationship between age and salary is 0.19, correct? I didn't put any asterisks over it. What does that mean?
It's not significant.
It's not significant. Really, there is no relationship between your age and your salary. How about relationship between years of experience, tenure, and salary?
There is a relationship.
0.65 and significant. I put one asterisk. If I put two asterisks, that means it is very significant at alpha 1%. If I put one asterisk, that means that it is significant at alpha 5%.
Now, if we are writing that, is there a special way that we're gonna say if it's extremely significant or just significant?
You don't
It doesn't
say that.
matter. One more time.
Look how nice I have put it in here for you. At the bottom of my table, I put one asterisk means it is significant at alpha 5%. Two asterisks, that means very significant. It's self-explanatory. I'm sorry, Nora, go ahead.
But Kirsten, correlation in here is just R.
Correct. These numbers in here, this is a, notice what Nora is saying. These numbers in here are the R's. These are the Pearson correlations. These are these numbers. I put these numbers. And then I did not put significance, I did not put N. In the text of my research, I put, there were 60 person in my experiment. Look how many times this 60 is repeated. It's annoying and cluttered. And I don't care about these numbers. I just put asterisks in here, clean, nice. Easy to read. Go ahead, Daniel.
So, let me try to phrase my question. So even if it's not significant, you're showing it here in the table?
Yeah, you need to show it in here. So the readers, they recognize that there is no relationship.
Oh, okay.
So yeah,
And you were saying that the two asterisks indicates very significant, so.
yeah, look at the under it, I have put, under the table, I put two asterisks means significant at alpha 0.01. So probably in here, let's say, do we have anything? But this is less than 5%, I put one asterisk. And here, look at this one, this number. Look, very strong significance, huh?
So,
So I put two asterisks so the reader knows that, look, this is really, really strong. Go ahead, Carlos.
Why is it that we can measure a correlation between the same variable but not be significant?
Correlation between a variable and itself, obviously,
Would be one.
that means, yeah, it's one.
Right.
There is no correlation between a variable and itself. Age and age.
But SPSS just doesn't give you a value for the significance when you compare
No,
values.
one is means perfect.
and is it ever perfect?
No, sometimes you will find, you may.
So when you're doing research, would you typically just do a Pearson correlation, or would you do another test? Like when you're trying to find, doing a study, would it be sufficient if you just run Pearson correlation test and then?
Yeah, you will find this exactly like this that appears in published papers. Yeah, you will see this kind of things.
But is that only if you want to determine a relationship, like not to
If there's
determine
a-
anything else?
If you want to do anything else, of course you run other things, as I'll show you in a minute. This is, you will run most probably you will run regression. But there are times that you want to run Pearson, and you will see that in published articles. All I want to know is whether you guys know how to read this table that I have in here. This is the same table. This is very cluttered. A lot of extra things you put in here. But the way that I have it in here, which is this is the way that it is in published, you get write a report, you do it this way. It is clean, no clutter, use asterisks instead of all of these numbers, put asterisks in here. Actually, computer does it for you.
So do you just
Check.
click the editor and then just take off the rows that you don't want in your presentation?
Yeah, sure, you can do that. You can double click in here and edit it, remove things, or I typed it myself, now that easier.
So you want it to look similar to this?
For your final exam, I don't want you to waste your time to give me this. Just go ahead and copy this in your Word and give it to me. But be aware that this is the right way to do
So
it.
if we were writing a report, that
When you write a report for publication or report, you do it this way, not this ugly table with a lot of clutter and junk in it. Jenna, I'm sorry, did you have?
Oh, no, I was just gonna say, because if we're using this table for a layperson, would it be better for the layperson to have percentages instead of decimals?
For the layperson, the text of your report should explain things. There's a strong relationship, or you can say is that our research shows that as, for example, years of experience of people goes up, the salaries are affected and goes up, something like that. But for a statistician, you want to have it this way so he can see the numbers. Or for the layperson, you may want to say, for example, that our research shows that 64% of the sales of ice cream is determined by temperature in the sea. And layperson can understand.
and R is not percentages anymore, right?
R is a percentage.
R squared.
Excuse me, R squared is percent, but this one, it just gives you that feel for your closer to here or closer to here.
And what's in the table is R, not R squared.
What is in table, these are the correlations. The correlation values, R's. R is in here.
So if we wanted to know the difference, we would just square the number in the Pearson correlation.
Not difference, you want
The-
to know that how much age affects how much age affects years of education. Then square this number, that's about what, 9%, 10%. If you square this number, and this tells you that age, or let's say that 10% of the age has to do with education. Doesn't make sense. Age and education.
Does SPSS give you R squared value, or do you have to calculate it?
You do it yourself. Go ahead, Thomas.
So does R squared give you does it factor in all possible variables or just only the variables within your data?
Only for these two variables that you have to study. How much of this variable causes variation on this one?
So if it's 60%, then you would say that 30%
Or
is.
40%.
Yeah, 40% would be caused by.
All other things.
All other
Not-
possible variables or all other variables in your data set?
No. You have looked at only these two,
Uh-huh.
60%. That means that 40% has to do with all other things that outside of these two.
Okay.
Shall we move on to the real stuff?
No, we're good. We're good. This is it. I like the one.
These are all warm up for what I want to tell you next. So, I don't think if I need to project it. So let's go back to our example of, let's say, temperature and sales of ice cream. Let's say this guy who is managing one of these ice cream places, he went to his records for last 365 days, and let's say this is sales, and here is the temperature in here. Temperature in here. Here's the January 1st. January 1st, the temperature was 31 degrees and he sold $592. January 2nd, the temperature was 32 degrees and he sold $685. January 3rd was, for example, dropped to 25 degrees and sold $491 and so forth. Temperature and sales of ice cream. So imagine now we draw the histogram of these two variables in here. Or a scatter plot, excuse me, scatter plot of. Let me put temperature in here and sales of ice cream in here. Here's the sales of ice cream and here is the temperature. Here's a convention. If you know the direction of causality, the one that is the cause, you put it in here in the x-axis. This is your x-axis. The one that it is the effect, or you want to predict it, you put it in y-axis. So it is temperature that is causing sales of ice cream, correct? I don't put sales of ice cream in here, temperature and heat. So this x, or temperature, we call it independent variable. Independent variable is your x. And then your y is a dependent variable. Remember, you have two variables in here, two columns. Each column is variable. One of them is your independent variable, one of them is dependent variable. We know that temperature causes sales of ice cream, or from temperature you can predict sales of ice cream. Oftentimes in the literature, very often you see that they don't call it independent variable, they call it predictor. So you will see that term also. And this one, oftentimes you see that outcome in the literature, you see it. But these are generic terms. So if you're talking to a biologist or chemist or economist, these are generic terms, they understand what you are doing. Like the word variable, all scientists understand what it is. Okay, here is, let's say, a temperature of, for example, 0, 1, 2, 3, 4, 5, 31, 32, 33, and then in Texas, of course, we may get to 115, for example, is the maximum. So in January 1st, the temperature was 31 degrees, and sales of ice cream, and remember here are the dollar amounts, huh? The dollar amount. On January 1st, the temperature was 31 degrees, and sales of ice cream was $592. Let's say this number, let's say this is 500 in here. 592 would be in here. So this is the point for it, huh? For January 1st. January 2nd was 32 degrees, which is right here, and was 685. Let's say this is 600 is in here, it would be somewhere around this area, huh? Then the other day, let me see, January 3rd is 29 degrees, which is in here, it would be somewhere in here. A computer will do this for you. It's like give you a scatter plot, bang, bang, it gives you. So let's say that you draw the points in here, and you can see relationship between temperature and ice cream, sales of ice cream, I have put them in this graph. Now, if you step back and take a look at these data points on this scatter plot, you can see that there is a trend in here. Huh? You can see that as temperature has gone up, actually, if you run a Pearson correlation, let's say you get positive 0.80, for example, relatively strong and positive. Huh? I can see that as temperature goes up, sales of ice cream has gone up too. And there are some variations in here. Go ahead.
Is it always like checking for a linear? Does it ever like check to see if it's exponential?
Curvilinear or no relationship? Yes, of course.
Or I mean like an exponential curve.
Yes, that's right. Absolutely. It's a log linear, curvilinear. It could be like this, or it could be like this, or it could be, yeah, it could be anything. But
And it's just so it's just checking to see if they're related along the same curve, not necessarily that's a straight.
we just want to make it easy.
Okay, I'm just.
But you are absolutely right.
Take the
You're
second.
absolutely right. That relationship might be curvilinear. Is there a relationship between tax rate and government earning? Laffer curve. Have you all taken economics? Are you all familiar with Laffer curve in economics? Tax rate, and that is during, if you were around during the Reagan administration. James and John, do you all remember Reagan? And,
I'm old, I'm not that old.
here is government earning. What's the government earning? So we know that
And I'm still in my 40s.
as the tax rate goes up, the higher the tax rate is, obviously government earns more money, correct?
Right.
Up to a point. Beyond that point, we know that as the tax rate goes beyond certain point, earning of government will go down. Like for example, if tax rate is zero, obviously government earns zero, correct? Government doesn't get any taxes, obviously it doesn't earn any money. If tax rate is 100%, every penny you earn, you pass it on to government. Guess what? How much is government earning? Zilch, nothing. Why should I go and work? I'll go to Florida and bask under the sun. Incentive to work goes down. So relationship in tax and government earning is curvilinear. So yeah, you are correct, but I was hoping that these issues will not come up because then we get into.
Sorry.
Is the same be said for sales of ice cream, because if it's like 130 degrees outside, if you could say have a temperature.
People do not go out to eat.
They
No,
don't
it
go
could be
out.
curvilinear, yeah. And let's suppose that this is what we see, right? It's simple. But I want to get to something. So, I mean, stepping back and saying, yeah, I know that number tells me that there is a positive relationship, and that shows me positive. As temperature goes up, sales of ice cream goes up. So that positive is correct. And it's 80. So it is this way, or it is not very sharp.
If they
So,
were, I'm sorry,
go ahead.
if they were going and it was a negative and they were going in different directions?
Yeah, if it was negative, that means that you get a line that is this way.
Um,
As temperature goes up, you see that this is going down.
Oh, because you would change the independent variable to.
No. The still temperature is in here, sales of ice cream is in here. But if it is negative 80, that means as temperature goes up, sales of ice cream is coming down. Like here's it for this. You increase the temperature, sales is less. The temperature is in here, sales goes up.
So just.
Yeah. But anyway, just eyeballing in here will tell you that, yeah, I know. It seems to me that as temperature goes up, sales of ice cream goes up, there is some trend in here. Now imagine, and this is cluttered in here, imagine mathematically, if you can find a line that goes right in the center of all of these numbers, I mean these data points, if you can find this, it's like an average, huh? Except linear average. Imagine you find a line that goes right in the center of all of these numbers. And don't look at this cluttered data point anymore. Just look at this line. And this is a lot cleaner to look at the red line. This line, we call it the regression line. It is that line that goes right in the center of data and is the linear average of these things, if you want to think about it. And I need to take you back to when you took Algebra 101. Remember, equation for a line is what? Y equal to A plus BX, or I think that if I remember when I was teaching my daughter and my son, was M and N. Is this what it was? I think it's in their textbook. But anyway, B is called slope. Is this line is this way, or this way? That B is the slope of this line. And that A is where this line intersects with your y-axis, is this area. If x is 0, this part becomes 0, y equal to A. So if the temperature is 0 right here, this is your A. And then the slope of this line, how steep it is, how flat it is that B. So I'll explain for you what, so the equation for this line is A plus BX. In statistics, we use A and B. A, we call it intercept. Because if X is 0, this line intercepts with Y at this point. So A is this much. B is the slope. What does that mean? The slope is that how much y goes up for 1 unit of x. If x is 1 unit, how much this line, how much y becomes? This is your b.
How did you figure out that number?
Which one? The computer will give it to you
Oh, in the table.
in the table.
Oh.
So let's say that these 500, let's say this number 365 numbers that guy collected from his past records, temperature and sales of ice cream. You put them into SPSS, very simple. Click the button and then it gives you a number. For example, it gives you a number, let's say 300 plus, for example, 20x. Y is sales of ice cream. X is temperature. So the equation for that ice cream place is this. The computer will give you this number, and what I want to show you is the interpretation of those numbers. I'll give you several examples. So this is the intercept. This is the slope. Let's interpret it. The 300 means that if this part is 0, temperature is 0. If this part is 0, y is 300. That's that if temperature is 0, so that part becomes 0, y is equal to 300. So if temperature is 0, that ice cream place sells $300. Still, there are some kids that want to go to my kids. No matter what the temperature is, they want to have ice cream. Some pregnant women, they want to have ice cream, craving for ice cream. So still they sell ice cream, even if the temperature is 0. What does that 20 mean? That is the slope. That means that for every degree, remember, our x is temperature, degree, correct? And then for every degree that the temperature goes up, sales of ice cream goes up by $20. So if the temperature is 31 and then becomes 32 degrees, all of a sudden you sell $20 more ice cream. If it moves from 32 degrees to 33 degrees, you sell $20 more. For every degree that the temperature goes up, I say goes up because this sign in here says that going up. For every temperature that goes up by 1 degree, sales of ice cream goes up by $20.
Does that only work for linear?
It works for linear.
It only works for linear though.
For linear.
It wouldn't work on that.
Curvilinear. Yeah, that's how much.
So sorry, you said
What
that
you want to
20,
do is that curvilinear, you want to convert it to linear and then, yeah,
You had to change your
yeah,
X and Y to.
yeah, that's right.
the 20 is the slope and you said 300 is the,
Intercept.
intercept? And how did you get the 300?
The computer will give you this. Computer will give you this. So you have 365 days of data. You put them in the computer. Computer will give you this. It gives you the intercept and it gives you the slope.
Will we see how those numbers come out? Like, where to find them on a table?
Yeah, I'll show you. We haven't done regression on the computer.
But it won't be like slope or intercept.
I'm sorry?
It won't be labeled.
Yeah, it is labeled and computer will call it constant. I'll tell you why they call it constant or intercept. So what I want you to understand what it is. 300 is the intercept, 20 is your slope. The meaning of the slope is that as x goes up by 1 degree, 1 unit, depending on what in this case is temperature. As x goes up by 1 unit, y goes up this much, this much. Let me give you an example. Taxi fare. You get in a taxi, they turn the dial $5 fixed. No matter where you go, for 1 block you go 10 block, that $5 fixed. But then for every mile that you go, you pay, let's say, $2 extra. So that $5 that is fixed at the beginning is this. And then every mile that you go, $2 extra will be added to it. That $2 is, think of it as a slope. For each unit of mile, you pay $2 extra. That's the meaning of this. So you put these things in a regression, you put those 360 numbers in a regression, and computer will give you this. Oh, computer will give you a lot of things. Most of the numbers are diagnostic, all these things. Like if you want interesting number that you may like it gives you this. It means that how much of sales of ice cream is related to temperature. It gives you 64. In here it gives you the R-score. That means that 64% of the sales of ice cream has to do with this bad boy.
I'm confused.
But I'm saying that computer not only gives you this
Oh,
number,
okay.
but also in addition it will give you this one as well.
So we don't have to calculate it?
You don't have to calculate, and then give you a bunch of other things, but this is probably the most important thing. That tells you what's the contribution of the temperature on sales of ice. Now this one, this is called bivariate regression. Bivariate regression. You hardly ever you do that. It's very unrealistic to look at the impact of one variable on another variable. Most probably, sales of ice cream is caused by many other things, huh?
Bless you.
Usually in statistics, there is one full chapter on this. I don't want to emphasize too much, so long as you got the big picture, I want to push you into multiple regression, which is probably more important. Okay, let's suppose that we know that sales of ice cream, has to do with temperature and I'm looking at the days. Unless it's every day, number of piece changes. Let's say, how about humidity of everyday now? You know, does humidity affects sales of ice cream? You know, it's raining. Let's say humidity, for example, just for the heck of it. Let's not read too much in it. Imagine I want to know whether sales of ice cream, how much of it has to do with the temperature of the day, how much of it has to do with the humidity. So on January 1st, temperature was 31, sales of ice cream was 592, and humidity was, give me a number. Let's say 80% humidity. And January 2nd was 91% humidity, and so forth, 62% humidity. I can run a regression, and I can visualize it for you. This one, when you have two variables, I can put it in this two-dimensional board. One for x, one for y. Now here I have three variables. If you can imagine this. Imagine the corners of this room. Let's say, imagine this corner would be my y. Sales of ice cream is this corner. And imagine on this corner I put all of the numbers for the temperature. In here I have all the numbers for sales. And in here I have all of the numbers for humidity. Three-dimensional. Can you imagine that? And I have all these numbers, and I get these numbers, and I put them in this space right here. Can you imagine? On January 1st, temperature was 31 in this corner, and humidity was in this corner, this much. Sales of ice cream was this much. Here are a bunch of numbers in this space.
But the point would be both the humidity and temperature with the sales.
Yeah, humidity and temperature are the two x's that I have in here, two corners in here on the floor. And then imagine my y is this vertical corner. And all of my numbers will come in here. Now if I, this one is easy to imagine, I'm going to make it even more complicated. Imagine if I put a plane that goes right in the center of all these numbers. I can see whether this plane is sharply going up or sharply going down, or it's tilted, is it tilted, is it tilted? But instead of thinking that way, which is complicated, computer will run a regression for you and give you the numbers. It's easier to understand. It gives you, let's say computer will give you a number as 250 plus, let's say 31 temperature. Let's say the first x is temperature, and then, for example, gives you 10 X humidity. Computer will give you two of these numbers for, you have two X's. One is temperature, one humidity. Gives you this number. So instead of thinking abstractly about the picture, in here, this is easy to look at it, two-dimensional. But when you have more than one X, in here we want to know the impact of humidity and temperature. We want to know the impact of these two variables on sales of ice cream. So they have two X's, one temperature, one humidity. The impact on one of your Y's. Imagine this is your Y, here is your X1, this is your X2. So you get a regression like this, and here's the interpretation of it. That's very important. And that is why regression is so important. It is the bedrock of statistics. This 200 means that if the temperature is 0, if this part is 0, if temperature is 0, and humidity is 0 too, this part is 0, this part is 0, you still sell $250. If both temperature and humidity are 0, that is this part and this part are 0, you still sell $250. What is important is the meaning of these two numbers. If you like, you can call them slope. In here, it makes, yeah, in here it makes the slope to plane, or thinking plane. Listen to this to see the importance of regression. This number, $31. That's for temperature, correct? It means that if we remove the impact of humidity, control for the impact of humidity, the pure impact of temperature is $31 on sales of ice cream. So for every degree that the temperature goes up, sales of ice cream goes up. Look at this is positive. Goes up by $31 if we remove the impact of humidity, control for that. And what is this number? And let's say if this is negative, so this, that means that for every percent that the humidity goes up, temperature, sales of ice cream goes down by $10 if we remove the impact of temperature. It would control for the temperature. If we get the pure impact of humidity, that's what we want to know. It would control for the impact of the temperature, remove the influence of it. Humidity, for each percent of humidity, we have measured humidity in percentages. For each percent humidity goes up, sales of ice cream goes down by $10. Remember, sales is a dollar amount, correct? So these are all in dollar amount. I'm sorry, Jordan, did you have your hand?
Yeah, I was just wondering, I don't understand that argument for equation of it goes up or down if you remove the influence of it. What are you talking about with that?
So up and down, I'm looking at this sign.
Okay.
Removing the impact, that means that in this case, for example, if